In this video, we're going to talk about integration by substitution. This is just going to be another technique that we can use to integrate functions. I've got this example set up for us, and while I'm starting and going through the beginning portions of this, I just want you to think about how are these two things related? How are these two parts of our integral related to each other? You may see it right off the top of your head. You may not. And that's okay. We'll just kind of keep it in the back of your head as we're going through, and maybe it will come to you. So we're going to start with a function f of g of x. This is a composite function. And we're starting here because we're going to kind of go through a chain of events here. And we're going to start by taking the derivative of this. We're going to take the derivative with respect to x. Now, when we take the derivative of a composite function, we have to use the chain rule. And when we use the chain rule, we get f prime of g of x times g prime of x. That's our basic chain rule for derivatives. We also know that integration is the inverse of derivatives, right? They play back and forth with each other. So if we were to integrate f prime of g of x times g prime of x with respect to x, we should get back to our original function. We'll get f of g of x, and of course we always add on our plus c, our constant of integration, in case there was something there. Now here we know, of course, that our c was 0 because that's what we started with. But if we jumped in right here at the integral, we don't know what c is, so that's why we added on there. Okay, so in this function, or in this integral, we are taking the integral of a derivative. Now normally we don't write this as a derivative. We just did that because that followed the flow of this entire line here. So let's look at it without that derivative. So we got f of g of x times g prime of x with respect to x. So we're taking the integral of this, okay? And it's still going to flow the same way as the second part of this top line, and we're going to get f of g of x plus c. Now, remember, this little f, this is just some function, and when we integrate this, what we're doing is we're creating a new function, capital F, saying that this is going to represent the area underneath the curve, generally from two different x values, and you know, we get into that in other videos, but that's why the notation is just ever so slightly different. But what if we called this g of x u? Now this is going to just change a little bit of the notation, but it's another way to look at this integral. So we're going to say we've got f of u with respect to u, where u equals g of x, and du is equal to g prime of x with respect to x. So this is just using substitution. Now this is where this integration by substitution is coming from. Okay, so what this is going to be is we're going to end up with capital F of u plus c. So we've still got the same thing. The only difference is instead of saying g of x and having all these extra parentheses, we've got a u in here. So we've substituted u instead of having the g of x. All right, so now how does all of this work together? Well, in our example, we're going to call u 3x squared plus 5x. Now, if you haven't figured it out by now, we're going to say du with respect to x is going to be 6x plus 5. That's just taking a derivative of u, of what we had. And that's also, if you notice, that second piece of the integral here. Now, what we're going to do is we're going to move this d of x over to the other side. So we've got 6x plus 5 with respect to x. So now we've got du equaling 6x plus 5 with respect to x. And this is kind of nice because now we have our u function and we have our du function, and we can integrate this thing nice and easy, just like we did right up above. So we can use it using composite methods with a g of x in there, or we can use it with u and du functions. I prefer the u and du, so that's what I'll be using. So this equals the integral of u to the fourth with respect to u. So 3x squared plus 5x, that's all to the fourth power, so it's u to the fourth power with respect to u. Okay, so now we're going to Yep, to the fourth power. So we are going to integrate this. We're going to use our basic power rule for integration. And that says 1 over 4 plus 1. So we take our n, whatever the power is of u, we add 1 to it, and we multiply that by u to the 4 plus 1, and we add our c in here. Very basic math, 1/5 u to the 5th plus c. But remember that u is actually 3x squared plus 5x. So we have to substitute that back in. So we have 1/5 3x squared plus 5x to the 5th power plus c. Okay, so how can we check to make sure that this is correct? Did we do everything correct? Well, of course, just like up above, we can take the derivative of this function, and that should get us back to what we were taking the integral of. So we're going to move this 5 over, and that's going to cancel out, and we're left with 3x squared plus 5x to the 4th power. And then we have to take, so this is now using the chain rule, remember, the derivative of this. So we take our 5 out, and then we take the derivative of the outside times the derivative of the inside, which is going to be our 3x squared plus 5. That gives us 6x plus 5. And we can see that that does match our original function, so this checks out. Okay, so let's look at another one. It's a little bit, it's similar, but it's going to be a little bit different. And let's say we have our integral of the square root of 2x minus 1. All right, well, first thing, anytime we've got a square root, we want to rewrite this using our exponents. So we've got 2x minus 1 to the 1/2 power with respect to x. Okay, so now we've got to set up what is u, what is du. All right, well, we'll start by taking u. We'll just take what's inside the parentheses there. So we've got u equaling 2x minus 1. So if we were to take the derivative of u with respect to x, that means we're just taking the derivative of 2x minus 1. So the derivative of u with respect to x is going to be 2. Well, just like in the example before, we're going to move that dx over to the other side, and we have the derivative of u is going to equal 2 times the derivative, or with respect to x. 2 with respect to x. Now, we have the integral of u to the 1/2 du. However, if you notice, this 2, when we did the derivative of u, that doesn't exist in our original problem. So when we use our substitution here, we have to make sure that we account for this extra piece that we've now included. This du is saying 2 times d of x, and we don't have a 2 in there, so we have to offset that. So how do you get rid of 2? Well, you divide by 2, or you can multiply by 1/2. So if we take our new substituted function and we multiply it by 1/2, that should offset that 2 that we've included now when we do du. All right, so let's take this through. We'll do a check on it to make sure everything balances out and see what happens. So as we integrate this, we're going to have our 1/2 times 1/2 plus 1. This is again using the power rule of integration. So we take the n, which is 1/2, add 1 plus 1, and u to the 1/2 plus 1, of course, plus c. All right, simplifying. We have 1/2 times, all right, we're going to do a little scratch work here. So 1/2 plus 1 is 3 over 2, and this is 1 over 3 over 2, which is going to be 2 over 3. So we have 1/2 times 2 over 3 times u to the 3 over 2 plus c. Well, our 2's can cancel out, and we're left with 1/3 u to the 3 over 2 plus c. Now keep in mind again that this u is equal to the 2x minus 1, so we have to substitute that back in, and we have our integrated function. Now, is this correct? Well, let's check. So we're going to check this by taking the derivative of our integral function that we just found. So we're going to multiply 3 over 2 by 1/3, right? We take that and multiply it on the front using our chain rule. Take the derivative of the outside. So 3/2 times 1/3 times 2x minus 1 to 3 over 2 minus 1, and then the derivative of the inside. And that's going to be, whoops, we're not canceling yet, that's going to be 2. So The derivative of the inside is our 2, so now we can start canceling our 3's. So we're going to cancel our 3's out, and we're left with 1/2 2x minus 1 to the 1/2 times 2. Well, of course, our 1/2 and our 2 also cancel out, and we're left with 2x minus 1 to the 1/2 power, and this does match what we originally integrated, so this is good. So this is a method, again, this is called integration by substitution. So we're using, we basically take a portion of our integral, of the function portion, something that you could graph on its own. We call that u, and then we find the derivative of it, substitute in, make sure we take care of any offsetting, and then integrate as normal. And it's always good to check your work. So I hope that helps, and we'll talk to you in the next video.